Welcome to Study Loop.
This is the answer to the Smith Organic Chemistry textbook, chapter 13, problem number 56. And this problem is asking us to consider why the carbonyl stretch for cyclohexanone is 1720, but the carbonyl stretch for 2-cyclohexanone, which is an alpha beta unsaturated ketone, is only 1685. And the answer to this problem is found by drawing the possible resonance structures for the alpha beta unsaturated ketone. And so I've drawn them down here. I've shown lone pairs of electrons and electron movement and charges in blue so that they're easy to see. So you have your first structure, and then this double bond can shift a pair of electrons up to the oxygen. So the oxygen will have a negative charge. The carbon that was formerly part of the carbonyl now has a positive charge. And then from there, the double bond can migrate. And so the oxygen would be unaffected by that, and the positive charge would just be down on this other carbon now. And so remember that resonance structures don't mean that these three molecules are distinctly present at any time. What resonance structures mean is that in reality, the molecule exists as some hybridization of these three structures. So that's another way of saying that there is not a double bond between these two carbons and a double bond between this carbon and this oxygen, that there is a partial double bond between the carbon and oxygen here in the carbonyl, a partial double bond between these two carbons, and a partial double bond between these two carbons where the double bond is originally drawn. And so a consequence of these partial bonds that the resonance structure is showing us is that the carbon-oxygen bond in the carbonyl, rather than being a typical double bond, it has some partial single bond character. And so because it is partially a single bond, it's somewhere between a single and double bond, probably much closer to a double bond, but not a perfect double bond. And so because the bond is somewhat weaker, what we see is the energy that it absorbs from the IR when it's bombarded with infrared radiation. It doesn't vibrate as strongly as a typical CO double bond. And so the signal that we get from it, the peak, is shifted down, shifted to the right. And so that explains why it's somewhat lower than a typical ketone. And so that is the answer to number 56.